Hello, everyone. I have discussed theory of linear regression. Now I'm going to demonstrate the applications, how to run linear and multiple linear regression in R. So R code will be discussed now, and I will run the R code for a data known as the D3. So let me start running the code. So I have a D3 data. So I run the D3 data. Let me check the variables of the D3 data, how many observations and how many rows are in the D3 data. If I check it H2, then I find that there are 1440 rows and 29 columns. If I want to take a look at the data sets, so here is the data sets. So it has a variable, race, income, age, smoke, and up until BPC, blood pressure category. So this is the class practice data that we have been using from the very beginning. But this data has a special characteristics. In this data, the ID has the unique ID. So there is no repeated measurement because simple and multiple linear regression model are not appropriate for the longitudinal data. So that is why from the longitudinal data, we selected the first visit of each person, and then we are going to feed simple and multiple linear regression model on that data. So these data, which is denoted here as a H2, does not have repeated measurement. Okay, so now let me erase any row that has a missing entries or missing values. So after deleting the missing values, let me see how much uh, rows are in there. Now it reduced to 1107. So the data H1 has a 1100 rows and 29 columns. So what now I'm going to do, I want to take a look at the scatter plot of the two variable DBP and SBP. So DBP stands for diastolic blood pressure and SBP stands for systolic blood pressure. When we visit doctor's office, when doctor take our blood pressure and then we see two blood pressure reading, one is high and one is low. High one is known as the systolic blood pressure and the low one is known as the diastolic blood pressure. So usually if a person is diagnosed, if a person is diagnosed with high blood pressure, both of his SBP and DBP will be up. If a person is diagnosed with low blood pressure or hypotension, then both of the SBP and DBP reading should be low. So for the high blood pressure, both of the reading should be high and known as the hypertension. For the low blood pressure, both of the reading of SBP and DBP should be low and known as the hypotension. Okay. So now we want to take a look at the scatter plot of the SBP and DBP. If we take a look at the scatter plot of the SBP and DBP, we see that there is a upward trend. So one is increasing, other is also increasing. We consider DBP in the x-axis and SBP in the y-axis, and we see certain kind of linear trend. So we want to fit a linear line on these data in order to predict like the future observations or new observations. We want to predict that. So first thing what I'm doing, this is the R code written as D1 LM DBP and then tilde SBP data H1. If I run this, we got the we denote like linear regression output as D1. And now I want to take a look at the summary of this output. So here is the summary of the D1. So when I write the summary, we got these things. So I need to explain some things from this output. If you take a look at that, intercept is 45.13. So intercept is this. That means beta 0 equal to this. And SBP, which is 0.28028, which is the beta 1 or slope. Okay, both of these parameter, intercept and slope, both of these parameter beta 0 and beta 1 are significant because p value is less than 0.05. You are seeing triple star in there, triple stars corresponding to like close to zero. So this is very small number. Okay, a very small number it is. So it has been written in this format. Now, come to the residual standard error is this, and the degrees of freedom is 1105. And we need to take a look at the adjusted R square value. From there, I need to give an explanation. So adjusted R square means 5% of the SBP is explained by the DBP. So 5% of the systolic blood pressure can be explained by the diastolic blood pressure. Remaining 95% are due to the other factors which are not included in the model. So, and F statistics is this. Overall, the model is found to be significant. Okay, so this is the explanations of the simple linear regressions output. Now, I want to do model prediction. In order to do the model predictions, I took some SBP value, which is known as the 110, which is known as the 110, 120, 115, 125, and 130. Okay. So here DBP was my dependent variable and SBP was my independent variable, and systolic blood pressure is always the higher reading one. When blood pressure measurements are taking, there are two reading. Higher reading is called the systolic blood pressure and lower reading is called the diastolic blood pressure. So we want to predict the lower reading when the higher reading is given. So we consider a higher reading value. That means new SBP value, new data value is 110, 120, 115, 125, 130. And we name it in this format. And the data is known as the SBP test. And I want to predict now. So see how the prediction R code is written. Predict D1. So D1 is the output from my linear model fitting. Here is the D1. Here is the D1. So I am predicting D1 for the new data. For the new data. So if I predict these things, I got this. Now take a look at that. This value will be smaller. All of these values is smaller corresponding to this value. When there are 110, the prediction value is that. When 120, the prediction value is little higher. When this is 115, prediction value is little lower. When 125, it is little higher. And then 130, it is more higher. Okay. So that means one is going up, other is also going up. So we have made some prediction. Now we want to do scatter plot with regression line for the SBP and DBP. So this is the way we can do the scatter plot. We plot from H1 data, we plot SBP and DBP. SBP is my independent variable, DBP is my dependent variable, and I am specifying the AB line in order to see the graph. So this is the graph. If you take a look at that, this is the graph. The graph is hiding within the R console and R editor. But if you press Control Tab, the figure will appear. And you see, I fitted this average line in here. Okay, this is called the regression, means all the times that you are predicting on an average. Unless if you want to use quantile regression, where we can predict on the different percentage values of the distribution of interest. That means the dependent variable. Okay. Uh, so this is the model fitting. Now the same thing could be done by alternative approach. This is the alternative approach by using ggplot. Ggplot is a very good package. Ggplot package. If you become familiar and become an expert of ggplot, then you can do many different kinds of graphing. So if I run these things, So we got these things. So this is the entire thing that we have used here to do plotting, okay, by using ggplot. So here, take a look. I took a little time, little pause. I here use geom smooth method LM. This linear method is being used. How this line was fitted, the this is called geom smooth, and method is linear model, and one is systolic blood pressure, another one is diastolic blood pressure, and here we specify like the this is my x, this is my y, this is my independent variable, this is my dependent variable. That way it is done. Now if I want to find the confidence interval for the estimate beta 0 and beta 1, that is the way you can find. This is the 95% confidence interval for the intercept, that is the 95% confidence interval for slope. Okay. So now after confidence interval, we want to construct the confidence band as well as prediction interval. So this is the we want to predict for a particular value. In such a cases, I have to write like this. So take a look at that. I am taking SBP equal to 93, and then I want to see the fitted value is 71. Standard error is this, DF is this, residual is this. Residual is the difference between observed and predicted values. That is called the residual. Residual has another name which stands for estimated error. So when we have X and Y, when we have an X and Y, we cannot estimate the error. From X and Y, you cannot. But after feeding the model, if we subtract fitted value from the observed value, then it will be the residual, which is known as the estimated error. So that's the way can get the um, we can get the point predicted value. Point predicted value. Now I want to take a look at the confidence interval of the regression line. So this is the confidence interval of the regression line. This is the confidence interval of the regression line. Um and that is the prediction interval. When prediction interval is computed, that is computed for the new data sets. Okay. So that is why I'm using this is the prediction interval. It is way bigger than the confidence interval. And this is the way you can find the residual, the difference between observed and fitted values. The fitted value is coming from model fitted. So if you write here residual, and then if you write here length, so 1100 something will be the length. Okay, so let me check. Length would be for residual D1. Like this, like that, and then residual. So these are the all residual. Okay, all 1100 values of the residuals is in there. Okay. So this is how did we obtain? We obtain it subtracting a predicted value from the observed value. Observed value means original Y. That means original DBP. Predicted DBP is subtracted from the observed DBP. Then we will get this residual. Okay. So we want to test whether residuals is normally distributed or not. In order to do that, if we run this, we see that p value is not bigger than 0.5, so residual is not normally distributed. But if we transfer this in the log scale, let me see what we will see. Uh, if we transfer this in the log scale, uh, um, okay, so log scale, so there is nan and warning is showing in there because residual could be positive and negative, and log cannot handle the negative value, right? So now in such a cases, if we put there apps, So now after doing the logarithm of this, it is still the p-value is um, p-value is very small. So residual is not normally distributed. We want to take a look at the box plot and histogram for the residual. So box plus a graph is hiding somewhere in my R. So if I press Control Tab, I will see. So here I see the residual. From the figure, it looks like a normal. Take a look at that. This is the median. This is the top 50%. This is the bottom 50%. Is from box plot and histogram, it looks like it is a normal distribution. So now if I want to take a look at the QQ plot, so QQ plot means what? What is my QQ plot? D3. It should be not D3, it should be H residual, right? Residual is coming from where? Residual. So just put the residual, nothing else. I want to put here just residual. This residual start with the capital R or a small r. Just take this. I want to put it in there. Now, if I do these things, you see, it looks like this. But if I run that one as well, QQ line, residual, let me do these things together. So that is not a good picture. That is a good picture. So take a look at that. So that means, um, what does this mean? This means I am putting theoretical quantile in the x-axis and sample quantile in the y-axis. What does the sample quantile? So sample quantile means the data that we have, that is our sample. So the residuals that we have, that residual is the sample, and we are putting this in the y-axis in the different sample quantiles, and in the theoretical quantiles I put in the uh, x-axis. So then theoretical quantile and sample quantile, if they construct a one straight line, one falls over the other, then it is known as the normal distribution. This is what known as the QQ plot also. Okay. So now that is the end of the discussion of the simple linear regression model. Now I am going to discuss about multiple linear regression model. So again, same data. And then in this data, I took SBP, WT, TC, TG, HDL as my independent variable. We want to see the combined effect of these four variables over DBP. And our summary statistics is showing us these things. From the summary statistics, we see that DBP is influenced by the intercept and SBP. So DB weight, total cholesterol, triglyceride, and HDL does not have any effect on DBP. Does not have any effect on DBP. Okay. So that means weight, total cholesterol, triglyceride, and HDL is insignificant on DBP. So that means they are not a significant factor to influence the DBP. So from the R square value, we see these things. So that means almost 6% of the variation of DBP is explained by the SBP, weight, TC, TZ, and HDL, and remaining 94% due to the other factors which are not included in the model. From F statistics and p-value, we see that the overall model is significant. So and after that, this is the residual I'm finding, and then I'm finding the residual in this format. And finally, I try to find the normality test for the residual. We find that the residual is not normally distributed. So residual is not normally distributed. Now box plot and histogram of the residuals has been drawn. So from multiple linear regression model, like a few outliers. from the box plot, but from box plot, top 50% and bottom 50% are shown in the figure. We like this is the median. So top 50% and bottom 50% is almost similar because the data is very big. So in such a cases, even though histogram and box plot showing a symmetry, but p-value is not giving us the value less than greater than 0.05. So we can say that data is not normally distributed. That means residual is not normally distributed. Okay, so box plot and done. So box plot, and now if I run the QQ plot to check whether they are normal or not, residuals are normal or not, we got this figure. This figure said that except in the extreme right tail and extreme left tail, so theoretical quantile and sample quantile shown there in the right tail and left tail, some observations are not coinciding with the sample quantile are not coinciding with the theoretical quantile. So data is not normally distributed. Okay. Okay, that's the all discussions about using simple and multiple linear regressions by R. So you can do your homework either by R or by Python. You have a freedom to do that. So, but that's the main thing. And all of these questions for the different data sets has been put in the homework problem. So this will help you to write the code for your own data and own variable, which is different from the data and variable that I have used in this video. So I think if you use this code, your homework will not be that difficult. Okay, I'm going to stop in here. Thank you very much. Bye.